So I'll talk about the Monte Carlo simulation with the help of FlowshopSim, which is my simulation tool. I use this one in this session. FlowshopSim is a very simple, user-friendly, and powerful and scientific software tool for a discrete event simulation of certain type of production lines. A simulation model of a production line in this tool involves only the following 7 factors at any workstation: the number of parallel lines, inventory limits, the average cycle time, statistical variation in cycle time, resource speeds, resource failures and repairs, resource calendars. So I'm not considering the rework, rejections, defects, and all these things in the simulation. The production line, this model is restricted to these 7 factors, but I feel this tool can still be quite useful to simulate a lot of production lines. Okay, now we can also this tool can also be used to simulate multi-product manufacturing. So I would run a few simulations, a few scenarios of production line now using this FlowshopSim. So I open this tool. So let me consider first a simple production line. Let me show. This is the one I'm going to consider. A simple balanced production line with no random variation in cycle times and no machine failures and calendars. So let us consider a production line consisting of 8 workstations. Assume that there is only one machine at every work center, and that machine is activated, operational. And let us assume that we implement a kind of pull system with inventory limits as shown in this column. In this example, the inventory limit is 5 at every workstation, and cycle time is exactly 10, say 10 minutes at every workstation, and there is no random variation in cycle times. Regarding resources, as I said, there's one machine at every workstation, and each one has a standard speed denoted as 1. If we assign, say, for example, 1.5 here as the speed, it means 1.5 times the standard speed. So if we assign 0.5 only, then it is half the standard speed. That's our notation. And let us assume that the resources are available right away without any delay, and no failures, no repairs, not even calendars. So I'm considering here the simplest production line. Is a balanced production line. So I'm going to simulate this trivial production line. Before I proceed, initially I want to show the animation of simulation for a few seconds. For this purpose, I uncheck this box. So let me simulate now. You could see how the pieces are flowing through 8 workstations. Well, this is not a sophisticated animation. It is a pretty crude one, but it's valid. It is scientifically valid, but it's crude. So we have to wait for a significant amount of time to see the completion of all 100 pieces with the animation. So therefore, I would skip the animation and let it run fast. Now we see the simulation output in summary. The line, the average daily production on the line is 134.58 pieces, and the line produces one piece for every 10 minutes. And the average WIP on the line is 7.48 pieces, and the average lead time of every piece is 80 minutes. So now let us see the material flow on the line through this Gantt chart. You can see the P1, the first piece that passes through 8 workstations without waiting anywhere. It takes 10 minutes at every workstation, and it does not wait at any workstation. And similarly, other pieces also, they flow through the workstations without waiting anywhere. So this is a perfect one-piece flow. And let me show the workloads on the resources. You can also see the simulation output through this chart. Here you see the workload of every resource. The R1, the machine at the first workstation processes the pieces in the order P1, P2, P, and other resources also the processes the pieces in the same order. So now, sometimes it may happen that, for example, the resource R4 is not available for some time, initially. Then the first piece is waiting for 30 minutes here for R4 because R4 will be available at the 60th minute instead of 30th minute. And then all other pieces will wait because it is a perfect one-piece flow. That is the design by nature of it. And for example, here R7, again, there is some delay, for example, then all other pieces wait there. So because this one-piece flow, it is not easy to recover the effect of these delays, initial delays. The only way we can recover is by increasing the speeds of resources.